Okay, so all of these things are different shapes. Let's see what you said. The easiest one that you've maybe seen before many times in a class is x1 squared plus x2 squared equals 1. Hopefully everybody or most people get this one. Hey, look at that. 19 people knew it was a circle. That's amazing. So let's start putting these in. I'm going to draw them in my favorite graphing calculator, Desmos. Desmos calls it x and y, but of course it's the same as x1 and x2. Can I shrink this a bit? Okay, there we go. Beautiful little circle. A little circle of radius 1. That is that. Okay, great. What about, let's do absolute value of x1 plus absolute value of x2. What do people think this one is? Ooh, okay, 17 people are in diamond and 2 people are in square. Let's see who's right. So again, once again, in Desmos, absolute value of x plus absolute value of y equals 1. And look at that, it's a beautiful little diamond. This is something I learned very well when my son went to kindergarten, is the difference between a diamond and a square. Okay, so what is a square? A square is when it's the other way, right? So the thing that makes it a diamond is a square rotated 90 or 45 degrees. So that's a diamond. Of course, technically it's a square as well. So if you said square, I guess you're not technically wrong. These other ones are more interesting. Let's see what people said for these ones. x1 to the 6 plus x2 to the 6. Ooh, okay, a little bit of a spread here. But most people picked a rounded square. Let's see what this one looks like. X to the power 6 plus y to the power 6 equals 1. And you get a beautiful rounded square, which is nice for making like buttons or something on a website. This is the kind of formula they use. And even more extreme is this one, the maximum of the two values. And 13 people again think this is a square. Let's see what it looks like. Does Desmos know about maximum? I guess we're going to find out. Maximum of x comma y equals 1. Oh, that's not a square. That's some weird L piece. Does anyone see what I did wrong?
Absolute.
Yeah, I forgot the absolute values. Okay, very good. We'll put them in. And there you go. Okay, so what does it look like? You can kind of see these things. They start on the inside and they kind of move out. All of these are balls in different metrics or different norms. So these things mathematically are called norms. These functions on the left-hand side are all different norms. And setting the norm equals to 1 is the definition of a ball. So let's write some of this down. So a norm tells you the length in quotes of a vector. And it's written like this. You have some vector x, which is x1, x2, and you do its norm. That tells you how long the vector is. But the thing about norms is there's more than one. The most common norm is the so-called L2 norm, or sometimes people just write 2, the 2 norm. And that is the regular Pythagoras norm, x1 squared plus x2 squared. Actually, this is the formula for the norm squared. So this is the square root of the norm. But there are other norms. I think this is the thing that you must know, is that this is not the only norm. And another one is the L1 norm. L1 norm. That is also called the 1 norm. That is the absolute value of x1 plus the absolute value of x2. So this is sometimes called the Euclidean norm, or Pythagoras norm or something. This one has a funny name. Does anyone know the name of this norm? I'm curious. You've seen it before. This one is called the Manhattan norm. The Manhattan norm. Why is it called the Manhattan norm? Well, this norm tells you how far apart things are when you're on a plane. So you're on an ordinary plane, and you're like, how far apart are these 2 points? You take the difference, you call that vector x, and you do the norm of x. That will tell you how far apart they are. What does the Manhattan norm do? In the Manhattan norm, you're not in the plane, you're in Manhattan. So here you are in the city. What does Manhattan look like? Yeah, like this? Okay, right? Okay, and then this is Central Park, right? You guys with me? Okay, Google Maps. We're gonna do it. Let's go. Manhattan. You spell it wrong. Okay, look, there's a picture. We want the map. Can I go to the map? Okay, first of all, everyone applaud my amazing picture. Look, see? There's the Manhattan, is this island, and there's Central Park, the little green thing. This is a masterpiece of art, okay? I did my PhD in New York, so somewhere down here is the Courant Institute of Mathematical Sciences. Let's see if we can find it. Yeah, here it is. This is where I did my PhD. Why is there a different norm? Okay, so let's pretend you're living in Manhattan and you want to go from here to here. Okay, let's take a little screenshot. Okay, so you're living in Manhattan and you want to move between places. Okay, so here we go. You're here. So Pythagoras, we know how that works. Let's pretend you're in Manhattan and you're sitting here at 18th and 1st, the 18th Street and 1st Avenue. That's where you start. And you want to end at 22nd and 3rd over here. This is where you want to end. Okay? So Pythagoras, or Euclid, says calculate this vector, call that vector x, and then do x1 squared plus x2 squared. That's like the length of this diagonal line. Okay? If you are sitting in Manhattan and you're sitting here, these are the city blocks, and you're sitting here, and you look at this, you have some angry curse words to say to Euclid and Pythagoras because you cannot walk this way. There are buildings in the way. All of these things are buildings. These are big buildings. Except, okay, the green parts are parks, but this is like a big building. You cannot walk this way. This is so stupid. You cannot do this. Okay? What do you have to do? You have to go up and over. So you can go like this, or you can go over and up. You can go boop, 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 boop. And then you can turn right and then go boop, 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 right? So if we get Google Maps directions from here to here, you cannot ever walk in the diagonal. There's buildings everywhere in between. Let me show the, can we see a layer? How do I do layers? There's a lot of pressure. Okay, there you go. Look at all these buildings in between, right? Look at these buildings. You cannot walk through these diagonals. There's buildings in the way. So you have to walk in this sort of a grid pattern. So how many steps do you have to walk to go from start to end? Well, this distance over here is the absolute value of x1, right? How much change is there in the x1 direction? Plus the absolute value of x2. How much change is there in the x2 direction? So the total distance you walk, total distance is x1 plus x2. And that is exactly the L1 norm. So that's why it's called the Manhattan norm. It tells you how many blocks you need to walk to get around in Manhattan when diagonals are off limits. So sort of the regular norm assumes you can just move diagonally, and this says you have to move in these directions. That's why it's called the Manhattan norm, or the L1 norm. Questions or comments about that? So now you know, when you see Manhattan norm, you know why. There's a whole bunch of these. You might notice a pattern. This is L2, this is L1. Maybe you can guess the general formula. The general formula is you do the LP norm. The LP norm of x is equal to the absolute value of x1 to the power p plus the absolute value of x2 to the power p. And then you take the pth root. So if you set p equals 2, you get the ordinary one. If you set p equals 1, you get the Manhattan one. But you can make all sorts of these. In particular, you can make p equals 6 was the example I gave. So p equals 6 is this one over here with the rounded green. And all of these things are setting the norm equal to something. So all these pictures are the sets where the norm equals 1. This is things that are distance 1 away. That are distance 1 away from the origin. Okay, so, and they look like different things depending on what p is. There you go, those are the different pictures. You can see when p equals 1, then walking to this place, that's 1 block over and 1 block down, is the same distance as walking 2 blocks. So this distance, going from here to here in Manhattan, is the same amount of work as going from here to there. It's 2 blocks either way, right? Whereas in Euclidean space, if you're allowed to go diagonals, you can go all the way down to here, and that's the same distance as going there, because you can travel straight down the diagonal, and you save a little bit of time. In the green metric, you can go all the way down here, and that's the same distance as going this. So you kind of get a boost by going on these diagonals in the green metric. You can kind of walk further than you can in the other one. There's one more, which is the purple metric, or norm. And this is another one, the maximum of x1 plus x2. And you might think this is some completely other one that has nothing to do with the other ones. But this is what is called the infinity norm. X infinity, or XL infinity. L infinity. The infinity norm. Why is it called the infinity norm? Because you can smoothly interpolate all these things. So if you do x to the power, in absolute value, x to the power p plus y to the power p, and you add a slider for p, set this equal to 1 to get a curve. Let's make it, what color should we make it? Let's make it orange. And then you see what happens as p gets really big. Let's go p from 1 to 100. And you see what happens. When p is getting close to 100, it smooshes all the way out. Let's see. Can I make this a bit smaller? Okay, there we go. Okay, maybe 100 was too extreme. Let me stop at 10. You're sort of connecting all these things. Okay, so p equals 1 is the diamond, and then you go through the circle, and then as you push out more and more and more, you get closer and closer to that square. And if you go up to big numbers, you get closer to that square. So here we go, getting more and more square-like. And that's because when you take something to a very large power, only the largest one matters. So between x and y, if you take it to like the power 100, then whichever one is bigger will sort of dominate the sum, and the other one is so small in comparison. So as the power p gets bigger and bigger, this gets closer to that. So that's the infinity norm. That one is also very important in different parts of math, this infinity norm. Okay, so now we've learned a whole bunch of norms. You might be wondering, what the hell does this have to do with data science? We're going to see in a second. But any questions or comments about norms? Yeah.
Go back to Desmos?
Yes. Yeah.
For the circle and the green rolling square,
Yeah.
the distance from origin to -1, 0 is has same length with the distance from origin to the bottom left of the green boundary.
That's right. Yeah. So this, you can think of this is the set of all the points that are distance 1 away from the origin, but we have different ways to measure distance, right? So the red is the ordinary way to measure distance. The blue is the way people in New York measure distance. And then, I don't know, this is some weird aliens that measure distance some weird way with the power 6. All these shapes are the set of all the things that are distance 1 away from the origin, but using different methods. And you can see that the point -1, 0 that you mentioned is always distance 1 away, but what happens on the diagonal depends on which way you're measuring distance. And the point is, for different problems, you measure distance differently. If you live in New York, you really do care about the number of blocks, right? Like when you put in Google Maps how to get somewhere, the distance it uses is this blue distance, not the red distance. You'll get the wrong answer if you use the red distance. Yeah. Other questions? So this is, why do we care about this? Because we're going to have to see something called Lasso regression. And the only difference between Lasso regression and ridge regression is the red circle versus the blue diamond. That's the only difference. So so it's just these two. In ridge regression, that's what we did before, also called L2 regression, we use the circle. And in Lasso regression, we're going to use the diamond. What do I mean by that? Let's go back to our formulas. The formula for the lasso versus the ridge regression, and this is why I think it's also better to call it L2 regression, or L2 regularization. What was the formula? So for every value of beta, we had a method to measure the loss. So the loss function as a function of beta, that was the mean squared error of beta. That's what we've been doing the whole course. But plus this alpha, and then we said, before we said beta 1 squared plus beta 2 squared, that's actually the L2 norm, beta of L2. I guess technically it's squared, but okay, it just changes the alphas if you have it or not. Let me put it in just to be consistent. So this is what we did before. Last time I didn't say L2 squared. I just gave you the formula, which was the square of the components, but that's really what we're doing. So what we are thinking of is we are thinking of this plane sort of being as the beta values. So you can imagine beta 1 and beta 2. And we're measuring how bad a beta is by how far away it is from the origin using the ordinary circle. So if somebody says, I think I want to use beta equals 2, 3, then you do 2 squared plus 3 squared, and you're like, your penalty is 2 squared plus 3 squared. Your penalty is 13 points. You get 13 points added on to your penalty, okay? That is this. I guess you get the square root of 13 points added on if you do the square, but without it, you do 13 points. On the other hand, we're going to make a new one today called the Lasso that you should have seen some videos on, and you know what's coming, which is alpha times the L1 norm, to the power 1. And the L1 norm says, don't penalize based on the sum of the squares of the beta, penalize based on the sum of the absolute values. And so if, in particular, if you have an example in the plane, if you have the point 2 across 3 up, then how bad is it? It's only 5 points bad, because you just sum the coordinates. And so this changes how we measure how much we penalize different things. And these balls will sort of tell you how they are. We're going to get into detail on using these in a second, or by the end of the lecture, and you'll see exactly how that matters. But that's the general idea. So all you're doing is changing this. Only difference changes here. So just how you measure for a particular fixed beta, you're up to you how to measure how bad it is, how much you want to penalize it. Regularization is this idea of adding a penalty term. This one is L1 regularization, and ridge regression is L2 regularization. That's the only mathematical difference. Yeah?
Sir, is the adding power in the ridge regression makes any difference?
Oh, adding this power?
Yeah.
It does not make any difference. The only thing it will do is reparameterize what alpha means. So if you have it with a square, then alpha equals 7 could be the same as alpha equals 1 without a square. So when you remember we had those plots last class, so we had the alpha on the x-axis and we were trying different things. Yeah. If you put it with a square or without a square, you'll just get a different shifted version of one or the other. In fact, it's like applying the square root function to the alpha value. And we're going to see that exactly later on as well. So yeah, this thing is totally just a choice to reparameterize this alpha. And it is nice, I will say it is nice to include the square because it makes the math easier. You'll remember last class, we were doing things like doing derivatives. And when you do derivatives, it's easier to do the derivative of the function beta squared than it is to do the function square root. So square root has a nasty derivative, so people normally keep the square, but mathematically it's totally the same up to changing values of alpha. We'll see that in a sec, actually, why it's the same. Great question. Anyone else? Okay. $1 million question. Why are you wasting my time with this? Who cares? You change the 2 to a 1. Does it make any difference? And the answer is, very surprising, is that the lasso has a very interesting property that the ridge does not have. And this is the main reason anyone would ever do something like this. There's only one interesting thing that happens, which is that this is the new interesting thing. Which is the lasso sets certain coefficients to 0. Or at least you could say more often than ridge. This is the only reason the lasso is interesting, is in ridge regression, we're shrinking all of the betas. So compared to without ridge regression, as you increase the alpha value, you're shrinking all the coefficients down to 0, but they never actually get to 0. They just get really small. In the lasso, when you do it, the coefficients literally hit beta equals 0, and they stay there forever. Let me show you what this looks like in the example we did before. Which is this, remember this hitters data set. So this is the hitters data set. This time I made sure to normalize it before I did anything. And when you normalize it, this was the graph we had before for ridge regression, which is all the coefficients here. They start out all different, and then as you increase the parameter, they shrink towards 0. They're never literally equal to 0. Right? You have these like smooth curves that go smooth and then smooth out, right? And they're getting closer and closer to 0 in this kind of like S-shaped curve, but they never literally hit 0. They just get very, very small. And I think I have even some things printed out. What is this? This simple linear regression. Do I have some of these printed? Yeah, trying different parameters. So here is alpha equals 1, and here are all the coefficients. Here is alpha equals 1 times 10 to the 10. So this is some crazy thing, and they're all very close to 0. I guess the computer stopped writing coefficients. This is nothing. Okay, I guess I want to rerun this with maybe something slightly less. Let's do 100 and hope that this runs. I ran this yesterday. Will it run now? Because 10 to the 10 was too big. The computer thought they were all 0. Let's make it 100. Okay, 100. Let's make it 1,000. Run it again. So the numbers are getting smaller. Let's do 10,000, add a 0. So the numbers are getting smaller and smaller, but they're not literally 0. So for example, this coefficient is 0.11. This coefficient is 0.03. They're getting smaller and smaller, but they're not literally 0. Let's add a 5 in front here and run it one more time. And now they're all less than 1. The coefficients all get smooshed towards 0, but they're not literally 0. And this is in contrast to the ridge regression. Or sorry, the lasso regression. So the ridge CV, we did that last class. Lasso is what we're doing today, and this is what the graph looks like. So as you increase the alpha value, you start out with the ordinary model. As you increase the alpha value, the coefficients, again, get closer to 0, but the shape of the curve is very different. They don't just smoothly get close to 0, they kind of slam into 0 and get stuck there forever. I think this one over here is a very nice one to see. It's going, it's going, it's going, and then all of a sudden, bam, it hits 0, and then it's stuck at 0 forever. And for alpha larger than this value, every single coefficient is exactly 0. So if you look at what these things look like, the shape is very different, and a lot of the coefficients are 0. By the way, you can do all the same things we did last class, right? Like plot the test error versus the parameter, find the minimum, things like that. All that is the same. That's all the same from last class, finding the minimum. But when you plot the coefficients, this is the thing that is different, is you have situations like this, where a bunch of the coefficients are exactly 0, and a bunch are non-0. And that is the only exciting thing about the lasso, is this parameter. Some coefficients are 0, whereas in the ridge, they're never exactly 0. They just get closer and closer to 0. That's the only difference. The rest of this class, everything we're going to do a bunch of different little mini activities. We're going to try to mathematically explain why is this true. So we're going to do the math to answer the question, why? And I think this is a very exciting math question you can ask. We changed one little mathematical property, right? We changed a 2 to a 1, and all of a sudden, we got this weird property that things are 0 more often. We're going to understand why mathematically. That's what we're going to do in the rest of the class. I guess before I explain why mathematically, it's useful to understand why is this useful. So why is this true is what we're going to do. Why is it useful? Why useful? It's useful because it eliminates variables. So imagine you have to pay a lot of money to record, to do tests. Like imagine each of these columns is a medical test that you have to do. It would be so nice if some of them were 0, because then you could just not do that medical test, right? If the coefficient is 0, you might as well delete it from your data set. So maybe you have a bunch of patients, and you run all the medical tests on your training set of patients. You do like 30 tests per person, and then you do the lasso, and the lasso tells you, hey, the only tests that you need to work on are the putouts and the years. Everything else doesn't matter. So you can eliminate some of the variables, and by eliminating the variables, that can help you in real life. So that is the main reason people want to do it. You get to eliminate variables. So I would say, why useful? Less variables equals easier to understand. Equals easier to understand. Maybe easier, cheaper. I could also add cheaper. So if you want something where you've selected some variables out, that's a good option. Of course, you can also do this with ridge if you do like explicit feature selection, like we did for project 1. You can take any model and just say, like, look at all the different subsets of features. So you can do this kind of by force, but the lasso does it automatically, and that's kind of a nice feature. Okay. Questions about why it's useful? All right, so let's see why it's true. And I'm going to try to explain this a few different ways, and hopefully one of them will stick with you. But it ultimately comes down to this picture, the warm-up problem. And it's going to be because a diamond has corners and a circle has no corners, that is going to be the reason why. This is going to be the ultimate reason. When you measure with the L1 norm, you get corners. When you measure with the L2 norm, there are no corners. That's going to explain what's going on. But let's see in more detail. So the first way I have of explaining this is more of the plot we did last class. So you remember this from last class, where we had in green, this was the loss surface. So as a function of beta 1 and beta 2, how much loss do you have? This is a 3D graph of this function. Right? The loss for ridge, that is the graph that is being plotted in green, the loss for the ridge. And the point is, here it is with alpha equals 0. Is this the right one? Maybe I want this one. Okay, yes. Okay, let me turn off some of these things. Let me turn off the data. And plot data, there we go. Okay, so this is the ridge regression loss surface. That big green bowl is the ridge regression loss surface. This little dot over here is the true value that we want to find, which is, I believe in this case, it's beta 1 equals 1, and beta 2 equals 4. It's the 0.14. And we're trying to find this thing. And we have this loss surface that tells you, for a given value, how much loss you have. And it looks like something like this bowl. Let me slide the alpha value around. Where's the alpha value? There it is. Okay. So when alpha equals 0, it's a bowl that lives just above the true thing. And as you increase the alpha value, you make this bowl wider, and you push it so that the center is more towards the origin. So if alpha is very big, the center is living above the origin. And in fact, what we're doing is we're just adding on, mathematically, we're adding on this function. So this is a function, and this is a function, and we're adding the two functions together. What does this function look like? You should know what this function looks like. Let's plot it. I have it here somewhere. It's the function alpha times x squared plus y squared. It's that gray bowl. And when you add the gray bowl to the original thing is when alpha equals 0. Where's alpha? I'm very zoomed in. Okay. So when alpha equals 0, you have this, and you're adding on nothing. What happens when you add on more? Let me actually plot it with nothing added on, so you can see both. Let's do that. So I want this function, and I want the part of the function that doesn't have any alpha. Let's add that as an expression. Okay. So let's call this function O for original. O of xy is the original mean squared error. And I'm scaling everything, so I'm going to plot O of xy divided by O of AB. So it fits nicely in our picture. And let's make this the original function. Let's make that in gray. Okay. Actually, let's make it in orange. Okay, let's do orange. So you can't see it right now because they're on top of each other. Let me scale the alpha a bit. Okay. All right, so what's going on here? Here's the little picture, and here's kind of what you should understand. Let's make this 0.01, and let's animate between these. So the orange bowl is our original loss function. That is the mean squared error loss function. It tells you for a given value of beta, how good are you doing? You want to find the minimum of that thing. But then we add on the gray bowl, and the gray bowl is a big parabola. It's like a big bowl that's centered at the origin, right? The gray bowl is exactly this function in 3D. It's the circle function in 3D. Because for every x and y, you calculate how far it is, but imagine this kind of pushed out into space with how far things are. That's exactly what the gray bowl is. So the gray bowl is how you measure things if you use circles and the ordinary Pythagoras. And we add them together. So we take the average of the orange bowl, which is what we want to minimize, plus the gray bowl, and that gives us the green loss surface for ridge regression, that is this function over here. This loss function over here is the combination of the original thing plus the bool we added on. Okay, and we saw last class what's the point of this? The point of this is that it moves things closer to the origin, and it's particularly useful when there's high correlation. So if you make the correlation very high, then the orange bowl becomes very weird and has this weird axis of being long in one direction, and by adding on the gray bowl, you kind of smooth it out, and you're closer to the origin, but you kind of are less stuck in this particular direction. That's all from last class. Questions or comments about the picture or what it represents right now? So now you got to ask yourself, when we switch, we're going to do the exact same thing again, and we're going to do it not for the ridge, but for the lasso. And so what will be different? There's going to be exactly one thing that is different, and that one thing is going to make a big difference in what happens. So what's going to happen, I'm going to again calculate the gray bowl. I'm going to add the gray bowl to the orange and see what happens. And that's over here in Lasso. So okay, let's leave the orange one on, turn off the gray and the green, and what does it look like? Well, here is the new function, which is the bowl. If you know what's happening, you recognize over here what's going to happen. You should have a prediction for what this bowl looks like. So predict in your head, what does the bowl look like when I turn this on? I'm going to turn it on in 3, 2, 1, boom. What is the bowl? The bowl is a pyramid. So before, we were doing circles, measuring how far away you are. So on the z-axis is how far away you are from the origin. And now it's still, again, how far away you are, but it's measured in this L1 Manhattan metric. And in the L1 Manhattan metric, you get squares as the cross-section, or diamonds, and so you get a pyramid that's being added on. So the thing we're going to do now is add the orange, which is the original loss function, to this pyramid. And that's going to give us the new loss function. So here we go. That's what it looks like. It's this purple curve. Actually, purple doesn't look very good. Let's change it to a different color. There's something I want you to see. Would it look better in blue? So there's something I want you to see. Okay, great. I think you can sort of see it at this angle. Let me try zooming in a bit. And let me fix an alpha value where it looks nice. Okay, so you start out by doing nothing, and then as you add on more and more of this thing, you change the surface. You change the surface. Let's add on a really extreme one, like this. And I want you to notice something really interesting about this blue loss surface. So now we're taking the minimum. When we do lasso regression, we're taking the minimum of this blue loss surface. That's the loss function for the lasso. And I want you to notice something. I think you can see it if you look on this angle. You see the blue surface now has corners. So because the red thing we were adding on, this pyramid, was pointy in some directions, the blue surface has corners. I'm not sure if you can see it on the projector. Do you guys see this little corner, like right here? You see how it's a little cornery? So what happens when you take the minimum of the blue function is that it will sometimes be on these corners. So because it has corners, the minimum of the function is more likely to happen at the corners. And that means when you do lasso, you're more likely to find a minimum that is somewhere where the corners are. Where are the corners? They're exactly the axes of the pyramid. So they're exactly on the axes. So this is the first way to see it visually. I'm going to write this down. The lasso, this is the observation, which is that the L1 norm has corners. L1 norm has corners. And specifically, if you plot as a function of beta of L1 equals z, so you make a plot, this is a pyramid. That's the red pyramid that we saw before. And that has corners on the sides. So unlike the bowl shape from before, that is a pyramid. And therefore, the lasso loss function, the loss of lasso of beta, has corners too. This lasso loss function is a sum of this L1 norm plus the original thing, so it's going to have corners. And when you find the minimum is likely to happen on a corner. Therefore, the minimum happens at a corner. This is not always true, but sometimes. And therefore, we're going to eliminate a variable. And that's because the corners happen to be exactly in the positions where one of the variables is 0. Therefore, some variables are 0 when on a corner. Okay, so that's the observation. So this is sort of like a picture explanation of why the lasso is doing things. It's because of these corners, and the reason there's corners is because the L1 norm is a square or a diamond, and a diamond has corners. Let me show you in action what this looks like if you have data. So far there's been no data. Let's turn on the data now and generate some data. So here is the data. So remember the orange, okay, I gotta give this a different name or a different color. Let's make that green. F is this, okay, plus alpha. Just let me write it without this. Okay. Okay, so when you have a data set, right, the orange is the true thing. When you have a finite data set, you don't get the true orange thing, you have a little shift of it, and that's the green thing. So the green thing is like you took 10 samples from the data set, you made a sample of size 10, and now you are looking at the loss surface of just that sample. Okay? And then you can ask your question, which is, what happens if you do lasso? What happens if you do regression? Let me turn off this and turn this off, and let me just focus on lasso versus ridge. I want to turn on the ridge. Where's the ridge? Okay, here it is. And let me play with the alpha value. Okay. Okay, so what's going on here? So I have a finite sample of 10 data points. That's the green loss surface. If you apply ridge regression, you don't get the true value of 1, 4. You get this value over here. It looks like 2, 2. If you apply lasso regression, you get this value, which is 0, 4. So it zeroed out one of the variables. And you can see what happens as you change things. Okay, so first of all, if alpha is really small, and here's the fun thing I'm going to do. I'm going to animate the data being generated by changing the seed. So here we go. We're changing the data set. And you can see how things are changing. Maybe I want to go this way a bit. Okay, this is why 3D is hard. Okay. And as you increase alpha, you can see what happens. So if you make alpha really big, everything is 0. But if you make alpha sort of just right, then the ridge regression is going to be a little bit closer to the origin, but it's not 0. On the other hand, the lasso, that's the purple dot, is often, very often, on the y-axis over here. And that's because that's the corner of the loss function, and it's finding this out. So what's happening is when you run your ridge regression, you're going to get 2 non-zero estimates. And when you run your lasso regression, one of the estimates is 0 about half the time, maybe more than half the time. And that is useful. You've sort of eliminated a variable. So I don't know if this is super clear, but again, it's all about finding the minimum of this function that has corners. So when it has corners, the corners happen to align on this axis, and that's what's going on. So there's the first picture proof. That's the first picture proof. We're going to do a different proof in a second, but the same kind of idea. So this is a helpful place to ask questions if you're confused. Yeah?
You mentioned that sometimes the minimum doesn't happen at a corner for the lasso.
That's right.
So in that instance, you have 2 non-zero coefficients.
You would have 2 non-zero coefficients, yeah. So it's not that it always does it. It sometimes does it. And there's going to be a question later on where we're going to have a situation where you can tell exactly when does it work, when does it not work. But yeah, this is the thing. It sometimes does it sometimes doesn't do it. And it really has to do with where are the corners of this blue function? Not this blue function. Is this the right function? Yeah, okay. So the blue function, right, it has corners. But the blue function, if it's the minimum might happen sort of above the green minimum if you don't add on enough lasso-ness, right? So you're adding that pyramid to it. The pyramid is what creates the corners. If you create the corners but they're not strong enough, then the original minimum is going to dominate. And if you make the corners strong enough, then the minimum of those corners will dominate. So it's just it's a question of strength. If you make it strong enough, it will always set everything to exactly 0. And if you don't make it strong enough, then it won't work. So in some sense, it's a question of strength. But we'll see a more accurate way to do it. But like if I make it really strong, then now it's almost always making one of them 0. So there you go. You see how it's if the regularization parameter is high enough, then it's always zeroing them out because the sort of corners of the pyramid are dominating the minimum of the other function. Okay. Yeah. Great question. Yeah. We'll see another answer soon as well. Anyone else? Yeah.
So in the video, like if there is real data set and all the features are contributing the target value, then Ridge will be perform better than Lasso.
Yeah, which one will perform better? It depends on the data set. So there's not that one is always better than the other one. And so they have pros and cons. Another con that was going to come up later, but I'll just say it now, is that Lasso is harder to compute. So Ridge is faster on a computer. And so if you want to do something where you have to run it a lot of times or a very big data set, then maybe Ridge is better than Lasso. Lasso is a bit slower. You'll see why later on. So they have pros and cons. It's not that one is always better than the other.
And Lasso like performs better when some of the features are only like contributing to target value.
Maybe, maybe not. So sometimes Lasso is better, sometimes it's worse. And I think you should think of it in terms of pros and cons. I don't think you should say, when this happens, Lasso is definitely better. When this happens, Ridge is definitely better. You should think of Lasso and Ridge have pros and cons, and for every particular problem, you try to balance the pros and cons for your data set and what you're doing, and try to find the best thing. There's no like, bam, bam, always do this. That will never happen. Yeah, unfortunately. Okay, great question. Anyone else? Okay, so let's see another way to think about this, which is the following. I made a version of what we just did, but I made it in Python instead of Desmos. And the reason I made it in Python instead of Desmos is I wanted to make this beautiful rainbow graph, which I'm very excited about. Okay, this is a graph. Again, it's a graph of the space beta 1 versus beta 2. So you think of the x-axis over here, or the x and y plane in this picture. Yeah, okay, this is a good one. The x and y plane in this picture. Okay, let me turn off some stuff. So I'm going to turn off the lasso for now. And I'm going to turn on the optimum. And I'm just going to change the alpha value. Okay, great. Okay. Okay, and I want to put f. I want to put this back in the f. Okay, give me 1 second here to put this back in the f. This plus this. Okay, so this is the sum of the ridge regression bowl, and the blue dot is the minimum. And as you change alpha, when alpha equals 0, you're doing nothing. That's the original function. Okay, you're doing nothing. And then when alpha equals like a really big number, then the answer is close to 0. You see? But in between, the optimal answer kind of makes a path connecting what you started with to 0. And so it makes this nice path that goes between them. And that's exactly what I've plotted over here. So this is a plot. When the ridge regression parameter is very small, so here it's -1 at this red point, then you are at the original minimum, which in this case is 2, 3. And when the ridge regression parameter is very large, like 10 to the 4, this is the log base 10 of the parameter. So when you set the ridge parameter alpha to 10,000, then all the coefficients are 0. And in between, you have this nice path. You can think of, as you vary this, you move the parameters towards 0. By the way, this is just a plot version of this kind of picture, right? So we've seen this picture before, right? As a function of the ridge regression parameter, it starts out with far away, and then you move in closer to the origin, and I'm plotting each one individually. And here I'm plotting them, there's 2 parameters, and they're on a plane. So that's what it's doing. Why am I making such a big deal about this thing? This is going to show us something interesting when you answer the following question. The question is, what does it look like? So think of the optimal betas, beta hat of alpha, as a function of the parameter. That's exactly what we're doing. So as you change the parameter, you get a different point in the beta plane. This makes a nice curve in the beta 1, beta 2 plane. Here's the question. Given a circle of radius beta 1 squared plus beta 2 squared equals c squared, how many times can the curve intersect the circle? Select all the possible answers. And in the picture that I have, you have this nice curve. But the question is, could there be a curve that looks like this? So here's the curve. This curve is definitely possible. And I'm drawing some circle that looks like this. And I'm thinking of it. And my question is, could it intersect more than once? Could the curve do this and hit the origin? So here's the x and the y axis. Could this happen? That's basically what I want to know. Could this happen? That's what I want to know. And I want you to think about the formula. Let me write down the formula. So the formula is the mean squared error of beta plus beta, the norm in L2 squared times alpha. right? That's the thing that we're doing. And what we're plotting here is the minimum over all beta of this. That's the curve over here as a function of alpha. So there's a couple different things you got to keep in your head at once, right? What is the alpha value? What is this function? What are we doing? But if you've been following along, hopefully it's all in there. And I'm basically asking you, could this happen? That's what I'm saying. Questions or comments about the question? Okay, let me see. Let me set you loose on this question and see how you guys do. Could it happen? 0 intersections, 1 intersection, 2 intersections, or 3 or more intersections. So how many times do you intersect some circle? How many times do you intersect some circle? Okay, actually, maybe I'll give it a minute 30. There's a lot to sort of hold in your head and figure out. Okay, I think a lot of people are still working, but put in your guesses. I'll give you like 20 seconds here, but we're gonna do a revote, that's probably. So put in your guesses for now, and then I will see what people are thinking, and we'll go from there on this thing. Okay, just a couple people have not yet answered. Okay. All right, let's take a look. Okay, 19 people answered. 12 people said 1 intersection is possible. This is definitely true. This is what we saw in the picture. So if you draw a circle of radius 1, you draw a circle around here, it intersects this curve 1 time. 1 is definitely possible. All right, don't beep at me. Okay. So 1, definitely possible. If you picked 1, good for you. Let's see. What else did people pick? Some people said 2 are possible. I guess the same number as 1. 9 people said 0 are possible. So out of 19 people, only 9 people said 0 are possible. Or 0 is possible, I guess is better English. But let's look at this example. Is 0 possible in this example? Anyone want to weigh in? Yes or no? In this particular case, could a circle intersect that curve 0 times? Who wants to say?
Like if the circle is big enough.
Yeah, if the circle is really big, right? You draw a big circle like this. How many times does it intersect that curve? And in fact, I can tell you what is big enough. Big enough is, does it touch the starting point? Right? So the starting point is when the regularization parameter is nothing, right? When alpha equals 0. Here it only goes down to 10 to the minus 1. But look at our function, right? When alpha equals 0, that is the start of the curve. So when alpha equals 0, that's the start. That's you just remove this term, you find the minimum, that's the ordinary minimum of the mean squared error. And when alpha equals infinity, or alpha goes to infinity, that is the origin. And any radius outside alpha equals 0 is not going to touch it at all. We know it's always shrinking in towards 0. The coefficients are always getting smaller. right? Why are the coefficients always getting smaller in ridge regression? Because you're increasing the penalty, right? If you increase the penalty, the coefficients can only get smaller. If they were going to be bigger, why weren't they bigger originally? So they can only get smaller. And so in fact, the critical value here is the critical radius is C equals whatever it was when alpha equals 0. The norm when alpha equals 0. So whatever the L2, whatever the original thing was, you set alpha equals 0, you find that point, that radius, any radius larger than that is going to have 0 intersections. So that's sort of like this circle. Anything smaller has at least 1 intersection. Anything bigger will have 0 intersections. So 0 is definitely possible. All right. A lot of people said as well so some people said 2 are possible. Some people said 3 or more are possible. Actually, this one was very unpopular. Only 3 people said that. So 1, definitely possible. 0, definitely possible. 2 and 3, we don't know yet. I'm going to let you revote. And I will tell you it's not both of these. Okay? So it's not true that both of these are true. One of them is wrong or both of them are wrong, but not both of these. So the correct answers are 0, definitely correct. 1, definitely correct. 2 and 3, question marks. I don't know. I'm going to let you revote. And now maybe you've thought about it. We've talked about it. Maybe you have a better sense of what is going on. And I want to see what you guys are thinking. Okay. I'm going to open it up again for a revote. Okay, exercise 2v2. Okay, it's open. Go ahead and think about this picture and how this curve connects alpha equals 0 to alpha equals infinity, how it is changing. Okay, let me give like 30 more seconds here to put in your final guesses. Okay, 10 seconds, 5 seconds. Put in your final guess here, and let's see what happens. Okay, let's reveal what you guys said. So 20 people answered, 19 people got the memo that 0 and 1 are possible. 2 and 3, we got 15 to 2. What's the true answer? Is that they are both wrong. They're both wrong. 2 is not possible. 3 or more are also not possible. So I don't know, maybe you guys got some weird hint from me that you thought, oh, 3, that's not possible, but 2 is. And they're not possible. You can explain why they're not possible for the same reason. So if you understand why 3 or more are not possible, the same logic applies for 2. Actually, 2 is easier to disprove than the other ones. So there's also a simple reason why it can't intersect twice, which is that if you have a path that starts here and ends here, it starts outside the circle and ends inside the circle, it has to touch the circle an odd number of times, right? If you go in and then out, then how are you going to end at the origin? So you can't go twice. Like, there's a very basic reason you can't do this. You can't. How am I going to end? How to end at origin from here? That's impossible. So 2 is definitely not possible, just based on like. This is a topological reason. But the real answer is you cannot touch the circle more than once because you are minimizing a certain function. So this is the true fact, is that each circle is touched exactly once. Each circle less than or equal to c, where c is that value, equals the norm when beta alpha equals 0, is touched exactly once. Okay, and where is it touched? I can even tell you where it is touched. It is touched at beta. You can think of this as a function of the radius c is equal to the minimum of the mean squared error of beta on the circle c, on beta squared plus beta 2 squared equals c squared. So not only is it touching the circle, but it's touching the circle wherever the mean squared error is minimized. So it's a very simple thing. If you understand what's going on here, the whole overall curve is minimizing this thing with a penalty term. And I'm saying look at all of the points where the penalty term is equal to c squared. So if you're saying on the circle c, so this is where beta 1 squared plus beta 2 squared equals c squared, what are we minimizing? Well, the ridge loss function, the loss for the ridge as a function of beta equals the mean squared error of beta plus beta 1 squared plus beta 2 squared times alpha. But look, you told me you're on the circle where beta 1 squared plus beta 2 squared equals c. So the penalty term is exactly c plus alpha times c. So everywhere on this circle, every time you draw a circle like this, every single point on the circle has the same exact penalty applied to it, right? If you're on this point, the penalty is whatever the radius of the circle is. If you're on this point, the penalty is whatever the radius of the circle is. All of these points have an equal penalty to be applied. And so when you say, please minimize the mean squared error plus some penalty, if the penalty is equal everywhere on the circle, where does it touch? It touches wherever the mean squared error is minimized. So this point is the minimum of the mean squared error amongst all the points on the circle. So this is the minimum of the mean squared error of beta on the circle. And you can do this for any circle, right? So if you draw some circle like this, then again, the point that you find is the minimum of the mean squared error on the smaller circle. Something like this is totally impossible because you have 3 different alpha values. So here is like alpha equals 1, here's like alpha equals 2, and here's alpha equals 3. Which of these 3 points, they all have the same penalty? Which one is the smallest mean squared error? Whichever is the smallest mean squared error should be the one point that it touches. How can it have touch here and touch a different point here? Which one has a smaller mean squared error? That point or that point? Whichever it is, it should find that one. So it's impossible to have multiple intersections because at every single point, you're just doing the minimum of one function, the mean squared error function. And the reason this works is because the circle is the same as the penalty we're applying. So when you apply a penalty that is based only on the radius of the circle, every single circle becomes just minimizing the mean squared error. Okay, so what's the punchline? You can only intersect one time, or 0 times if you started further outside. You can never intersect once or more, and in fact, you can reparameterize the whole thing by just thinking of these circles as getting smaller and smaller. Let me draw this last thing, and then I will pause for a second if there's questions. So what is the point over here is instead of thinking of ridge as a function of alpha, that's how we've been thinking about it for now, function of alpha. And when you think of it as a function of alpha, you increase the alpha value and you get this path that goes like this towards 0. That's exactly what we got in this picture and how we've been thinking about it so far. You can equally well think of it as a function of the radius c. So ridge as a function of alpha, or you can think of ridge as a function of radius, as a function of radius, Okay, so in this picture, as a function of alpha, we were doing the minimum of alpha times the L2 norm squared of the mean squared error of beta plus this. So for each alpha value, we did this. Right? So we said alpha equals 0, alpha equals 1, alpha equals 2, and we made this whole curve, right? Sort of all these different points. So alpha is changing as you go, and you kind of moosh in. Another way to do it is to think of it as a function of radius. So you draw a bunch of circles like this. Here's the radius Here's the radius equals 1, radius equals 2, all the way up to radius equals the starting point, C. So here's 7. And what you do is you minimize the mean squared error on the circle over and over again. So for each radius, beta 1 squared plus beta 2 squared equals C squared, you just minimize the mean squared error. The mean squared error of beta. Minimize as a function of beta on the circle. Beta on circle. So this was beta anywhere. Minimize beta anywhere. And this one is on the circle. And there's no, you notice there's no term. If you wanted to add a term, it wouldn't change anything. If the term is constant on the circle, it's like adding 7 to the thing you're minimizing. It doesn't change it. And if you do that, you get a bunch of points. So you get a point over here, a point over here, a point over here, a point over here, a point over here. And the punchline is these are the same exact curve. So this is the same thing. Same curve. And why are they the same curve? It's exactly because we used the same penalty function, the beta squared penalty function, as we used to make the circles. And so on every circle, the penalty function is a constant. When you minimize over a circle, that is a constant term, and that's why it all works. So these are two different ways of looking at this curve. One as a function of the alpha parameter going, and one as a function of the radius. And it's the exact same thing. It's just two different ways of thinking of the function. And in fact, I think even in the textbook, they have some plots where they change the x-axis. So they have plots that look like this one, where instead of the ridge regularization parameter on the x-axis, they have the radius of the circle. And it's exactly the same thing. It's just squished a little bit. The x-axis has changed, but otherwise, it's exactly the same curve either way. Okay, we're about to use this fact in a second to see why the lasso is zeroing things out. But questions about this? Once you understand this picture, this is sometimes called the dual view of optimization. This is dual optimization. And there's in a lot of optimization problems, you can think of it in the original variables or the dual variables, and they're the same thing. This is the point. Let's do this exact thing, but not for ridge regression, but for lasso regression, okay? And for lasso regression, it's going to be the same thing. So for lasso regression, here's the picture that I want you to think. You have the axis, and what you're doing is you're drawing circles, but circles are now diamonds. So for every diamond, you will find, so for each radius, and radius just means the value of this diamond, for each diamond, find the minimum of the mean squared error. Find the minimum of the mean squared error. Okay, so maybe the minimum of the mean squared error over here happens over here at this point, and then it happens over here, and then it happens here, and then you get a curve that looks like that or something. Okay, and that is exactly what the lasso is doing. It's finding, for each possible diamond, it's finding the minimum of the mean squared error. And I made a little Desmos to kind of demonstrate this. So here's my little 2D Desmos. This little bullseye is supposed to represent the layer lines of the mean squared error. So remember, the mean squared error is like a big bowl, and to figure out where you should imagine this bowl coming out, where is it touching this thing first? So if this thing's over here, then you can imagine this is some like layer line, like you gotta imagine this coming out into space. This is where is the mean squared error minimized on this diamond? And the answer is wherever this touches for the first time. So it touches on the corner. Look at that. So the mean squared error in this case is minimized at this little corner over here. If the center of the bowl is somewhere else, then we're going to get a different answer. So for example, if the center of the bowl is here, then the mean squared error is minimized right at that point. That's the point, wherever this thing touches. And so this is assuming a circular mean squared error. In general, the mean squared error is not a circle, it's some kind of ellipse, but this is a special case. Here's another example where the mean squared error is minimized exactly at that point, right? So there are some examples. Is the sort of picture clear of like this thing is supposed to represent the bowl coming out of this shape, and we're finding where on this diamond is it minimized? Does it make any sense? Questions?
What if the circle is like inside the diamond?
That's a great question. So if the circle is inside, then the minimum, once again, if the circle is inside, that's the situation the absolute minimum of the mean squared error anywhere is the very center of the circle. So now you're looking at a diamond that contains the absolute minimum. That is exactly like the situation we started with over here, where we were doing it 0 times. Right? So if you start off with a circle that's like further outside than the starting point, then you have 0 intersections. So you can do it, but it's sort of excluded. It's like the case of 0 intersections for the value being larger. So you can do it. I mean, it'll still be the same picture, but the real answer is like it'll be the very center. That's what you'll get if you run the regression, and there'll be like no penalty term applied. But I mean, yeah, okay. Great question. Any other questions? Yeah.
So given what center of the circles, you might have the case where the lasso has no 0 coefficient.
That's exactly right. So depending on where the circle is, you will have different cases where either you're getting a 0 coordinate or not, and that is exactly the next MathMatize question, is which regions make it 0. So consider optimizing a purely circular mean squared error. That's this little bullseye, okay? In 2 dimensions, beta 1, beta 2. The ordinary mean squared error has a minimum at beta 1 star, beta 2 star. That's exactly the center of the bullseye. So I'm thinking of varying where is the actual true minimum, okay? You apply the lasso and are optimizing under the constraint that beta 1 plus beta 2 in absolute value equals 1. That is the purple diamond. So you're saying where on the purple diamond is the minimum of this bowl of a loss function that has its true minimum here at the bullseye. Okay. This makes a diamond in the plane and naturally divides the plane into 8 regions labeled according to clock notation below. Okay, here's the clock notation. So I labeled the regions of the plane. There's 12, 130, 3, 430, 6, 730, 9, and 1030. Those are the different regions that you can make. And the question is, which regions will the lasso eliminate one of the variables? There's some kind of error over here. But depending on where the minimum of the bullseye is, the lasso will eliminate variables. Which regions will the lasso eliminate a variable? And you have all these options. You should select all the regions that apply. Which regions will the lasso eliminate a variable? I'll give you like 2 minutes to try it, and then we'll take it up after that, and that'll be the last thing we do today. Okay, is the question clear? So once again, it really is all coming down to this picture and understanding this mean squared error bowl, which we started with, and understanding you want to find the minimum on the diamond. Okay, and if you copy this URL, you can play with it yourself. I believe I linked it in the thing. I'm not sure if you can go to the link. Yeah, here's the link. If you copy it, you can also play with it yourself and try.
So when you have some of the mean square errors centered around one exactly, coefficients, and some of the coefficients were already close to 0, that's why it tends to be.
Well, so this question is going to, once you answer this question, I'll say it's in this region. And one of the interpretations of the special regions are the ones where at least one coordinate is close to 0. So I mean, yes, for a certain sense of the definition is close to 0, and the sense is these regions. Yeah. Yeah. Okay. Let me give you guys 1 more minute, and then we'll take it up. I'll just tell you the answer in 1 minute, regardless of how you guys are doing. But it's a good check to see if you're understanding what's going on here. So we're sort of building on things as we go, right? Like if I had shown you this bullseye, like 2 classes ago, you'd be like, what the hell is this bullseye? But hopefully you've understood this loss surface thing, and you can understand the bullseye as a sort of slices of a 3D thing. And you can understand that we're trying to minimize on this little place. And hopefully it all makes sense. And we'll see if you get the question right or not. Once you sort of see the pattern, it's not so hard. All right, 20 seconds left. Get your guesses in. And remember, you should choose all the ones that apply, where the lasso is eliminating a variable. Okay, time's up. Put in your final, press your final submit button, and let's take a look at what people said. Oh, okay. Oh, I gotta zoom out. Okay, 13 people said 12, 3, 6, and 9, the whole numbered things. 4 or 5 people said the opposite, right? The correct answer is exactly what the majority said. 12, 3, 6, and 9 are the regions where the lasso eliminates a variable. Let me show you why in the picture. So if you start up here, you're asking, where is the intersection going to be? And the answer is at the corner, right? So when you're in this region, the intersection happens at this corner. And at this corner, notice the x value is 0. So the x variable has been eliminated. And that kind of logic at the corners is exactly where a variable is eliminated, works for any of these regions. So if you're anywhere in this region, you're going to hit the corner as the first thing you do. In contrast to that, if you're in this little narrow strip over here, then the first place you hit is somewhere on the side. And it can be different places on the side, so maybe it's further up or further down. Further up or further down, but it's somewhere on the side, not on the corner. And so for that reason, these regions over here are the regions where the lasso eliminates a variable. You can interpret these regions as places where, quote, one of the variables is smaller than the other one. So sort of in this like strip over here, where it's not eliminating the variable, the two values, the x value and the y value, are pretty similar, right? X equals y is exactly that diagonal line, and it's not far from x equals y. In contrast to that, when you're over here, the x value is a lot closer to 0 than the y value. So if the x value is closer to 0 than the y value, then you'll be in this region and you'll eliminate a variable. In practice, right, you change, here I did x plus y equals 1, but in practice you would also change that, right? That's like the size of the alpha you use, the strength of the regularization changes how big or small this diamond is. And so how big or small this diamond is in combination with what is the true values that will set whether or not things are being set to 0. But this is, I think, a good way to see it. If one of the coefficients is small enough, if you're in this region above the corner, then the minimum happens at a corner, and that's what the lasso will find. Okay, hopefully that made a little bit of sense. You saw it a few different ways with corners or this, and it all comes down to the diamond having corners, right? If you do the ridge regression with a circle down here, it's a very boring question, and you see exactly why for a ridge regression you don't get this corners property, but for the lasso you have these special corners, and that's what causes the variable elimination. Okay, let's stop there, and we'll see you guys on Monday. Don't forget to work on your projects between now and then. Okay.